mathematical form where these are partial derivatives. And in that kind of a coordinate system, if you manipulate the Einstein equations that I have not written down, by technique similar to what I did to derive that formula, you get the analogous formula with the stress energy pseudotensor for the gravitational field, which involves derivatives of the metric coefficients, along with the stress energy tensor for the matter, playing the same role as the stress energy tensor for the matter over here played by itself. And then it's a mathematical, a page of mathematical calculations to go from here to this same formula over there involving the mass quadrupole moment.
So how many lines in Landau-Lifshitz does that take?
Landau-Lifshitz gives the entire argument in about 2 or 3 pages. And the number of pages of papers that were written about this topic in the West over that period of time was, I would guess, 10,000. So, well,
yeah, that's interesting.
Yeah. Now, I should warn you in connection with this that my standards for levels of rigor are not as high as some people's. I'm a physicist and not a mathematical physicist and not a mathematician. And so I think there are those in the mathematical physics community who, having read Landau and Lifshitz and having perhaps understood it as it was meant to be understood, were still not satisfied. Okay. But at the level of rigor that I would normally require, and that the vast majority of physicists, including theoretical physicists, would require, Landau and Lifshitz is a very correct analysis. Okay, so henceforth, without going through the details of that, just having told you that that's how it goes, henceforth we will use these formulas to compute gravitational waves from slow motion sources, usually slow motion weak field sources. And this, in fact, is the leading order term in a multipolar moment expansion, as I discussed in the introductory lectures. So if you have a system that has rapid internal motions, then you've got to include the higher order terms, the mass octopole moment, hexadecapole moment, the current quadrupole, current hexadecapole, octopole, and all the rest. Okay. But even for a highly relativistic, very fast internal gravity system, if you want a quick order of magnitude estimate, this formula is the thing to use. Now, there can be circumstances where the mass quadrupole moment is suppressed and the higher order moments dominate. And there's a very important such circumstance that has been a subject of extensive work in recent years, which is what are called R-mode oscillations of neutron stars. And we will talk about that source later on this term. But it's very rare that this term is suppressed, and usually this is the dominant term. Okay, any questions? Okay, then I want next to begin a discussion of propagation of gravitational waves through the real universe with all its lumps and space-time curvature and matter. I'm going to begin by a discussion of propagation through vacuum, and I will on Wednesday, in the latter part of Wednesday, and on the problem set, we will deal with interaction with matter. But I'm telling you now that interaction with matter turns out, as we will see, to be utterly unimportant so far as propagation from the source to the Earth is concerned. And so what we're going to be doing today is, for all practical purposes, the full story. So the basic idea is that we have gravitational waves not propagating through flat space-time, but propagating through a curved universe. So that, for example, we can think of the universe as perhaps being closed, though we now know observationally that if it's closed with a very large radius, very large radius of curvature for the spatial curvature. But let me draw it as though it were the surface of a balloon. This is nice to deal with conceptually. We have the gravitational waves propagating through, which means in this heuristic diagram, propagating as ripples on the surface of the balloon. And the key thing that you notice as soon as I have drawn this little diagram is that the wavelength of the gravitational wave is lambda, and the radius of curvature of the universe, r, differ enormously in length scale. That the wavelength is very, very small compared to the radius of curvature of space-time. You notice that, of course, this is the opposite kind of relationship to what I used when I derived the mass quadrupole formula. Over here I used the slow motion approximation, which said the wavelength was huge compared to the size of the source. So we typically are in a situation where you have a little tiny source, a pretty big wavelength, and then an enormously big universe. And that's the regime we normally operate in. And for the purpose of discussion of the wave propagation, what I really need is that the wavelength of the waves is small compared to the radius of curvature of space-time. And that radius of curvature of space-time in the case of our universe is about the Hubble distance. In the case of the galaxy, it's something like 1,000 times the size of the galaxy. I forget precisely. In the case of the solar system, the radius of curvature of space-time is huge compared to the solar system. And so under all practical circumstances, with the kinds of wavelengths and gravitational waves that we're talking about, this will always be true. Under all practical circumstances. There are very special circumstances, such as when a gravitational wave that has a size, say, of a few kilometers encounters a black hole whose size is a few kilometers, then this may break down. But the fraction of the universe that is occupied by black holes with size a few kilometers, or by black holes at all, is an exceedingly tiny fraction. And so for almost all of the universe through which the waves propagate, this will be true, and they may very occasionally encounter a tiny localized place where it fails to be true. This is what I need in order to do the discussion that I want. In fact, it turns out this is what you need in order to derive wave propagation at the speed of light. As soon as you have a situation where the wavelength of the waves is comparable to the radius of curvature of space-time, then the waves fail to propagate freely, they're trapped, and they don't behave like waves at all. And we will see that later on when we do cosmology and look at the parametric amplification of vacuum fluctuations coming off the Big Bang, and say in inflationary cosmologies. As I say, under almost all circumstances this is true, and this is the condition you need in order to get out a wave equation propagation. So let me get that wave equation propagation out now. So I want to begin, in order to get a wave equation, with the formula that you have derived on the homework for the Riemann tensor as a wave equation for the Riemann tensor in generality, where no approximations were made. That formula, you will recall, says that the Riemann curvature tensor with a curved space wave operator acting on it is equal to terms that are of the form of the Riemann curvature tensor multiplied by the Riemann curvature tensor. So it's, let me write it in this form, where this ampersand, which I often use, means just plus terms that have this form, up to numerical coefficients and up to organizing indices appropriately. And so there's an exact version of this that you derived on the homework, I think, for last week, if my memory is right. Is that right? That was on the homework last week. And I want to now specialize this to the case of gravitational waves whose wavelength is small compared to the radius of curvature of the space-time through which they propagate. So in order to do that now, I need to separate the Riemann tensor into a gravitational wave piece and a piece associated with a background space-time. And the way in which I do this is to define the radius of curvature of the background space-time just to be equal to the average of the full Riemann tensor over scales somewhat bigger than a wavelength. Now, precisely how you do this average is something that a mathematician will worry about, but I think a physicist will feel comfortable that there must be some way to do this average that will be rigorous. And the actual method of doing the averaging is called Bril-Harville averaging, because it was derived by Dieter Bril and Jim Harville when they were students of John Wheeler's back before my time, slightly before my time. In a classic paper in Physical Review. And so they sort of laid the foundations for doing this. And the Bril-Harville averaging is discussed in an exercise in Misner, Thorne, and Wheeler, but that's a level of mathematics that I just don't want to get into in this course. So you can just imagine that it should be possible to devise a way to do the averaging. It basically says you've got to take the Riemann curvature tensor at here, there, parallel propagate the Riemann curvature tensor to a common point and then do an ordinary average. Is basically how you do it. Okay. So, and then you attribute this to that region over which you've done the averaging. So that tells us what the background radius of curvature of space-time is, and then the gravitational wave contribution is by definition just the full Riemann tensor minus the background contribution. And so, in order of magnitude, the background radius of curvature, or a Riemann tensor, has a magnitude that is 1 over the radius of curvature of space-time squared. So in the case of a smooth universe, this would be 1 over 10 to the 10 light years squared. It's 1 over the Hubble distance squared, 1 over the size of the universe squared. By contrast, this is the piece that is associated with a gravitational wave, and it's going to have a magnitude of the magnitude of the gravitational wave divided by lambda bar squared. Lambda bar, remember, is just lambda over 2 pi. Okay. So let's just look at some numbers in the case of the universe. This would be 1 over, so a light year is about 10 to the 18 centimeters. 10 to the 10 light years is 10 to the 28 centimeters. So this is 1 over 10 to the 56 centimeters squared for the universe. For the gravitational waves that I think we're going to detect, this would be 10 to the minus 22 divided by the wavelength of the gravitational waves, which may be 1,000 kilometers or so, something like the size of the Earth in the case of LIGO. Take lambda bar, 1,000 kilometers. So 1,000 kilometers is 10 to the 8th centimeters squared. So that's 10 to the minus 2 minus 16. That'll be 10 to the minus 38 reciprocal centimeters squared. You notice that the curvature tensor associated with the gravitational waves is big compared to that of the curvature of the universe in this example. Just in this example. Even though the gravitational waves are very, very weak. It's big because despite having a tiny amplitude, the wavelength of the waves is also quite small compared to the size of the universe, and that compensates for the tiny amplitude. So while you might have thought the way you want to analyze gravitational waves in a circumstance like this is you just treat the waves as having a curvature that's tiny compared to that of the universe, then you linearize in that way. That's not going to work because the curvature associated with the waves is, in this case, big compared to the curvature associated with the universe. And so, in fact, to do a mathematical analysis, the mathematical analysis is an expansion at a different small quantity. The mathematics is basically what is called a two-length scale expansion. It's an expansion in ratios of lambda bar divided by r. Two-length scale expansions are extensively used in physics and engineering, though often that fact is not brought out very clearly in physics classes. They underlie, for example, the analysis of boundary layers in fluid mechanics. As fluid moves past a body, you expand in ratios of the thickness of the boundary layer to the size of the body or the size of macroscopic aspects of the flow. And here, gravitational wave analysis is a two-length scale expansion in the ratio of lambda bar over r. Okay. Now let's look at what this two-length scale expansion means in the case of our wave equation for the Riemann tensor. If I go back to the wave equation for the Riemann tensor, the first term is r alpha beta gamma delta semicolon mu mu. I want the wiggly part of this. And this semicolon involves connection coefficients that have both a gravitational wave piece and a background piece. The gravitational wave piece gives me things that are sort of quadratic then in the gravitational wave field. So when you go through, you see that they contribute negligibly. And so I really want to take a double gradient with respect to the background space-time geometry, not with respect to the full space-time geometry. And so I'm going to use a slash to mean you're taking these derivatives as though you're doing field theory on a curved background. And it's the background whose metric is the one associated with this background Riemann tensor. So that's the first term for the gravitational, I'm sorry, this should not be background, this should be gravitational wave. I'm looking at the wiggly part of it. I'm trying to get a wave equation for the gravitational waves. Okay. You should shout at me if I do something stupid like that, or at least politely speak up. Okay. Okay, and then let's look at these terms. These terms, something that's quadratic in the gravitational wave field is obviously going to be unimportant. So what I need to be concerned about, most concerned about, is the gravitational wave piece, and then multiplied by the background space-time curvature. And that represents a coupling of the gravitational waves to the background curvature, and in fact it is that coupling that's responsible for strongly amplifying waves that come off the Big Bang in an inflationary epoch of the universe. Just this coupling. But we're in a circumstance where this coupling is unimportant, because if we look at the magnitude of the typical term in here, this magnitude will be the gravitational wave Riemann tensor divided by lambda bar squared, because there are two derivatives, and this gravitational wave Riemann tensor is varying on the length scale lambda. And this background space-time curvature has this magnitude 1 over the radius of curvature of space-time squared, 1 over r squared. And so we have the first term looks like gravitational wave Riemann over lambda bar squared. The second term, gravitational wave Riemann over r squared. And so the second term is negligible by virtue of our two-length scale expansion, our two-length scale assumption that this is small compared to 1. So this guy is big and that guy is small. And so what we do is we throw away the curvature coupling term. It's negligible when we are in this short wavelength limit.
Could you say again what that slash is? Or maybe.
Okay.
What would the connecting coefficients look like?
Okay, so let me go off. I was going to need this in a minute. I'll go off and do it right now. Suppose that I do for the metric the same thing as I have done for the Riemann tensor. So I want to go into a coordinate system that's as smooth as possible, so I don't have any artificial ripples in the metric coefficients. So in a coordinate system that's as smooth as possible, I can write G alpha beta background is the average of G alpha beta over a few wavelengths of the gravitational waves. I can then write the full metric as being G alpha beta background plus a gravitational wave contribution, which I will call H, because if I were in a local Lorentz frame of the this would be the flat metric, and my perturbation away from the flat metric I've called H before. Okay. So the slash means the gradient or covariant derivative computed using the background metric, whereas the semicolon would be using the full metric. And what I did was I said, I'm going to use only the background metric to evaluate this wave operator acting on the Riemann tensor, because the contributions that come from H are going to be very small. I've just asserted that. That come from, so the difference between using this guy and the semicolon is an issue of including terms that are proportional to H.
Why are they small?
Because H is small. So H is like 10 to the minus 21. And so when you go through, the fact that H is tiny means those contributions will be negligible. Now, if you really want to do this all, you can do it all and work out the full details. It would just take me 3 times as long if I were to do it at the board, but that's the key idea. So the bottom line is that we get a wave equation that says that the gravitational wave contribution to the Riemann tensor satisfies a wave equation. This is in vacuum, of course. All this was in vacuum. Satisfies the wave equation in the background space-time. So it propagates as though it were just a field living in the background space-time. Let me go back and make one other remark that I should have made earlier when I talked about the relative magnitudes of the actual Riemann curvature tensors in the 2 cases. The situation is very much like the situation on the surface of an orange. On an orange, the amplitude of the little bumps is very small compared to the size of the orange. But the radius of curvature of the little bumps, the little bumps have strong curvature. The curvature of the little bumps is a much stronger curvature than the curvature of the orange, even though the height of the bumps is tiny. Okay. And so the curvature of the bumps being big compared to the curvature of the orange is like the gravitational waves being big compared to the background in terms of Riemann tensor. But in terms of the size of the bumps, the gravitational waves are very weak compared to the size of the universe, basically. So that was a remark about what I said up here earlier. Okay, so I have sketched out a derivation that says that the Riemann tensor in a curved space-time for gravitational waves of short wavelength propagating through a curved space-time, the Riemann tensor satisfies the wave equation, just an ordinary wave equation, but it's the wave equation using the connection coefficients of the background space-time. I could have simply asserted this was true in another way. We know that if we go to a local Lorentz frame in this of the background space-time, in this situation where the wavelengths of the waves are small and the background curvature is huge, I can cover many wavelengths with a local Lorentz frame of the background space-time. And in that local Lorentz frame of the background, using a frame big compared to the wavelength, So its size of the frame is big compared to the wavelength of the waves, but it's small compared to the radius of curvature of the background. And that local Lorentz frame, as we have argued last week, the wave equation looks like that with partial derivatives. But if that is the formula correct in a local Lorentz frame of the background, then the corresponding frame invariant equation is this one. We just replace commas by covariant derivatives or curved space gradients. That's how we go from a flat space formula to a curved formula, except for conceivable issues of curvature coupling, which is why I actually went through this argument to see that the curvature coupling was unimportant. Okay. So in order to analyze this wave propagation, I actually don't want to use this version of the wave equation. I did my argument this way because doing it this way I didn't have to worry about gauge issues. But it turns out to be easier to use a wave equation for H in actually analyzing the propagation than to use the wave equation for the Riemann tensor. And so what I want to do then is take my gravitational wave field, as I might call it, which is defined as the difference between the true metric and this background metric, where the background metric was defined as an average of the true metric. So that is my H. I want to take that, and I want to now impose Lorentz gauge conditions on it by wiggling my coordinate system appropriately so that I get then H alpha beta slash beta equals 0. So I'm now doing my mathematics just as I discussed with the Riemann tensor. I'm doing it mathematically as field theory on my curved background, where the slash then involves the connection coefficients of the background. Okay. So this is Lorentz gauge. It's 4 conditions because alpha has indices 0, 1, 2, 3. And I can achieve those 4 conditions by adjustment of my 4 coordinates. And in that Lorentz gauge then, the Einstein field equations, we know in a local Lorentz frame, they would reduce just to H alpha beta, and a wave operator on them is equal to 0. And so by just the same argument as I went through over here, my ex post facto argument, my argument after I had done it somewhat carefully, it must be true that in my curved space-time situation, it will be true that the full coordinates, which however are constrained to be Lorentz gauge coordinates. It must be true that the Einstein field equations become H alpha beta slash mu mu equals 0. And that's not at all surprising, shouldn't be surprising. If the Riemann tensor satisfies a curved space wave equation, surely the metric perturbation does. The Riemann tensor, after all, is basically going to be constructed by applying a couple of derivatives to the metric perturbation and then doing some appropriate symmetrization of indices. And so a wave equation on this guy is basically going to be equivalent to a wave equation on that guy. What I want to do now is to very quickly solve this wave equation, making use of the fact that the wavelength is small compared to the radius of curvature, but imposing one other condition as well, and that is that the wavelength is also small compared to not just only the radius of curvature of space-time, but also small compared to the radius of curvature of the phase fronts of the waves. So I want to imagine these waves propagating through my curved space-time. The phase fronts look like that. They have a radius of curvature L. I'm drawing it in some embedding space, some flat embedding space. The whole universe is like the surface of this sphere. And I want to require both my original condition, the wavelength be small compared to the radius of curvature of space-time, which is this guy, and that the wavelength be small compared to the radius of curvature of the phase fronts. And this will be true if I'm far away from the source, unless I've run into a gravitational lens that has produced a caustic, which is a separate issue that one can discuss, and that we will discuss later.
Which direction are those waves propagating? Just kind of make sure I understand.
Well, I guess they're probably propagating in that direction since the curvature is like this. Yep. Though they might have gone through a lens and they might be propagating down and converging, conceivably, but
all this is saying is that the waves are about parallel.
They're about parallel. They're locally plane. They're nearly locally plane waves. Under these circumstances, I can search for a solution using what is often called the iconal approximation. So if you go to books on mathematical physics, you find general discussions of the iconal approximation. It's also sometimes called just the geometric optics approximation. And in this approximation, what we do is we write H alpha beta as a product of two terms. There is a slowly varying amplitude. This varies on the scale L or R or both. And then there's a very rapidly varying phase, so e to the I phi, and phi varies on the scale of the reduced wavelength of the waves. And then I'll take the real part of this because I'm using this complex notation, and in general this could be a complex amplitude. So you do this in electromagnetic theory. Many of you will have seen this done in electromagnetic theory. You do it when analyzing any kind of wave. This technique is useful in analyzing sound waves in the earth, seismic waves. This is a useful technique. Okay. Let me go off to the side here and note that in a local Lorentz frame and for monochromatic or nearly monochromatic waves, neither of which I'm assuming over here, but in that special case, the phase phi will be equal to omega times z minus t. I'm assuming the waves propagate in the z direction of this local Lorentz frame. That is, it's just the waves go like cosine of omega z minus t for waves that propagate in the z direction. Okay. And let's also notice that in this case, phi comma z is omega, phi comma 0 is minus omega. So if I define the gradient of phi to be k, so let me, so grad phi equal k, that in fact is the wave vector, because this is kz, that's k0, and so if I raise the index on k0, k up 0 is equal to omega equal k up z. So that in fact is just the components of the wave vector. that you would use in analyzing the wave propagation if it were a truly plane wave in a local Lorentz frame. And so by analogy over here, I want to introduce the gradient of phi. It's the gradient defined using a derivative that involves the connection coefficients of the background space-time, or it's a frame-independent gradient in the background space-time geometry. And that is defined, or I define K to be that gradient. Okay. Now let's look at the consequences of the Lorentz gauge condition. Lorentz gauge condition, well, let me, in fact, because time is running out, what I'm going to do is tell you the result of a little calculation that I will do on Wednesday. Okay? So, and the key that underlies this is the fact that this guy is varying extremely rapidly, and so the wave vector is huge compared to 1 over L or 1 over R. A huge wave vector, high frequencies. I call it approximation. And using that, then, we can write out the consequence of Lorentz gauge and the consequence of the wave equation and collect terms by sizes. And it's basically an expansion, turns out to be an expansion in lambda bar over R. It's this two-length scale expansion. We collect terms by sizes. When we do that, we see that H alpha beta slash beta equals 0 tells us that A alpha beta slash A alpha beta K beta vanishes, which says that the gravitational wave field is orthogonal to the propagation vector, orthogonal to the wave vector. It's transverse. This is a piece of the transversality that we have found when we did the analysis in flat space-time for weak waves. And the vanishing of the wave equation, or of the wave operator on H, is straightforward. In fact, I may not do it on Wednesday because it's so straightforward. I may leave it to you to do it. This implies two things. It implies that K is null. That's what you get at the leading order in this two-length scale expansion. And at the next order in the two-length scale expansion, you get that A alpha beta slash mu K mu is equal to 0. So in words, the first relationship, which comes from the Lorentz gauge condition, says the waves are transverse. They're orthogonal to the propagation vector. The second relationship says that propagation vector is null. And the third relationship says that, well, before I discuss the third relationship, let me derive quickly something that follows from this being null. If I take the gradient of that, I get K beta slash mu. That's 2 K beta slash mu. But K beta slash mu is the phase slash beta mu. And gradient indices do not commute on vectors, but they do commute on scalars. As you can see by actually going to a local Lorentz frame, they will commute on scalars, just not on vectors. And so I'll commute those, and that becomes phi slash mu beta. And so this becomes 2 K beta. Phi slash mu is K mu. This is K mu slash beta. So that says, that vanishes because K is null. So the thing I was differentiating was 0, and so the gradient is 0. And what this says is the derivative of K along itself vanishes. Del K, K equals 0. So that actually follows from the nullness of K and from the fact that the K is the gradient of the phase. This says that K is a tangent to a null geodesic then, this plus the preceding one. And what this says is that the waves are parallel propagated along those null geodesics. That says the derivative along k of A vanishes. And so this is what I will discuss on Wednesday. In this geometric optics or iconal approximation, the waves are characterized by this amplitude which is parallel transported along curves, and those curves are null geodesics. And that is precisely the same result as you would get for electromagnetic waves. And it is that, which is, I say, I'll discuss on Wednesday, which guarantees that for gravitational waves, as for electromagnetic waves, you can be gravitationally lensed by passing around the sun or past a galaxy or a star. You have gravitational redshifts, you have cosmological redshifts. All the phenomena of that sort that you have for electromagnetic waves, you have for gravitational waves. So we'll discuss it on Wednesday.